So first of all, thank you very much for inviting me to this seminar. So as just introduced, my name is Yuto Bekki. I'm a postdoc at the MPS, Max Planck Institute for Solar System Research. And today I'll be talking about numerical modeling of solar inertial modes. And this is largely based on my PhD thesis research, which was supervised by Robert Cameron and Lauren Kizon. Oh, sorry. Yep. So we are interested in the interior of the sun because there are so many interesting things going on. The turbulent convection and the resulting dynamo, these are not very well understood. And from an observational point of view, the interior of the sun can only be studied with helioseismology. So what we do in helioseismology is to observe and analyze the waves or oscillation at the surface to infer the internal structure or properties of the fluid. And historically, P modes or acoustic modes have been extensively used to do that, to do the helioseismology. They are stochastically excited by turbulent convection in the convective envelope and can be very clearly identified at the surface. We also have G modes in the deep interior, the radiative interior where the stratification is convectively stable. And both of these modes are really high frequency modes of oscillation with the oscillation periods of minutes to hours. But recently, we also successfully detected another types of global modes of oscillation called Rossby modes or inertial modes in more general. The restoring force of the inertial modes is the Coriolis force. So therefore, they have longer oscillation periods comparable to the solar rotation periods. So, so in short, they are very slowly varying phenomena. And that's why you need a very long-term observation to successfully characterize them and detect them. And now we have the observations from GONG, MDI, and NGMI. So now we have the observations with more than 10 years or to 20 years. So now it's a very good time to study the inertial modes of the sun. And they have very different properties from conventional P modes. So we expect that they can be used as an alternative tool to do the helioseismology. All right. So as I said, inertial waves are waves whose restoring force is Coriolis force. And Rossby waves are a special type of inertial waves. So, but what characterizes the Rossby waves is that they are global scale waves of vorticity arising from the conservation law of potential vorticity. And here the potential, do you see my cursor? Maybe. Okay. So the potential vorticity is defined by this. So it's a component of the absolute vorticity divided by background density. And Rossby waves can be classified based on the so-called beta effects, which is an appearance of the Coriolis force in the vorticity equation. So if the equation, the vorticity equation can be reduced to this form, the following form, and then the propagation direction of the Rossby waves is determined by this. So it depends on the sign of the beta effect. And in the sun, we will, in this talk, we will focus on the following three types of Rossby waves, Rossby modes. The one on the left is the classical Rossby or R mode. The one in the middle is the thermal Rossby, and the one in the right is the topographic Rossby. So the classical Rossby modes or R modes are retrograde propagating modes of radial vorticity originating from the planetary beta effect or simply beta effect. These are essentially toroidal mode, meaning that the horizontal motions are dominant over the radial motion. So they are essentially non-convective modes. The thermal Rossby modes are progradely propagating waves of Z vorticity, where the Z denotes the axis of the parallel to the rotation axis. And they originated from the compression of beta effect. So the background density stratification is crucial for their mode excitation. And they are convectively driven. The last one, the topographic Rossby modes, are the modes strictly confined inside the tangential cylinder. And they propagate in a retrograde direction because they originated from the topographic beta effect, which is basically the spherical shell curvature effect of the inner spherical shell. And when they're observed at the surface, they only appear at high latitudes on the sun or at the surface. So some people, yeah, they are also sometimes called high latitude modes. And in the sun, the classical Rossby modes are very, very clearly observed recently. And the thermal Rossby modes are really controversial because they are repeatedly reported in numerical simulations, but from solid observation, they are never successfully observed for some reason, and we don't know why. And the topographic Rossby modes are very little attention has been paid so far on these modes in the context of the sun's convection zone. But we will argue that they are very relevant to the polar spiraling flow of the sun. So we're gonna take a look at those modes independently. So now first, the classical Rossby modes. So these are very, very clearly observed. So here I show the radial vorticity power spectrum, the sector mode, the L equal M component of the spherical harmonics. It is a power as a function of azimuthal order M and the frequency. So it's basically the K omega diagram. And we can clearly see that the strong power concentration is, the strong power reach is lies on this theoretical linear dispersion relation of the sectoral Rossby mode. But we note that the sectoral ones are the only observed one. For some reason, we cannot detect the non-sectoral R modes on the sun. So even though the dispersion relation shows the sectoral mode, when you look at the latitudinal eigenfunction of the observed Rossby modes, you can see that the eigenfunction, so eigenfunction peaks at the equator and then it changes sign in the middle latitude and then it decays, which means that the solar Rossby modes also show some non-sectoral contribution represented by these sign changes of the shape of the eigenfunction at middle latitudes. And so the theory needs to explain these observations. The thermal Rossby modes are very well-known phenomena in numerical models. So here I show an example of the numerical calculations, and they are seen as north-south aligned lanes of downflow across the equator, and that are propagating in a prograde direction faster than the local differential rotation speed. And these are also called like Busse columns or Taylor columns and so on, banana cells. And so, yeah, so for people working on numerical models, they are really well-known phenomena, and what is important is that they play very, very important roles by transporting thermal energy and angular momentum in the convection zone to establish to drive the solar differential rotation, like with faster equator and solar poles. But the problem is that, as I said, they are not observed for some reason on the sun. And I think this is closely related to the convective conundrum, which is the biggest mystery in the solar physics. All right. And for the topographic Rossby modes or high latitude modes, as I said, they are not really discussed so far in previous literature, but we will argue that they should be closely related to some solar observations, which was already reported but misidentified so far. So here I show the observational snapshot of the non-axisymmetric component of the longitudinal velocity. And you can clearly see that there is spiraling flow pattern around the poles, which is largely m=1. And in the previous literature, they are argued to be the giant cell convection. But in this talk, we will argue that they should be identified as the topographic Rossby modes or high latitude modes that are paraclinically unstable. I'm gonna get back to this point at a later slide. All right, so so in this talk, I'm gonna present 3 different numerical approaches to numerically model the inertial modes in the sun. The first one is the linear analysis, and the second one is the fully nonlinear turbulent convection, rotating convection simulations. And the third one is still is also not strongly nonlinear calculation, but in the mean field approach. And I want to emphasize that these 3 approaches are complementary with each other. So let's begin with the linear calculation. So what we did here is to solve the linear. So here I show the linearized hydrodynamic equations in the sun's convection zone. This linear model is, I would say, more realistic than any other existing models because it takes into account the spherical shell geometry, differential rotation, the turbulent diffusion and latitudinal entropy variation, the non-adiabatic stratification, and so on. And what we did is to convert these linearized equations into a form of the eigenvalue equation with the r theta using the finite difference method for the r and theta derivatives with the r theta grid mesh. And for the background stratification, we use the sort of model S, and for the differential rotation, we use the profile obtained by global helioseismology. And so in the next slide, I will start by showing the results from the ideal case where there's no viscosity, the stratification is purely adiabatic, and the differential rotation is switched on. And then we we examine the effects of this turbulent diffusivity and differential rotation and entropy variation. All right, so this is the result from the ideal case. So on the left, I show the dispersion diagram. And on the right, I show the eigenfunctions of the 3 components of the velocity and pressure perturbation. So positive frequency, the real part of the eigenfrequency, corresponds to the prograde propagation, the phase propagation, and the negative corresponds to the retrograde. So the equatorial Rossby modes with no radial node, n equals 0 mode, is denoted by red, and the thermal Rossby modes by blue, and the topographic Rossby modes by green. And yeah, that's the expected results. So in addition to these fundamental modes, we also discovered the so-called mixed Rossby modes. So here I show the eigenfunctions of the equatorial Rossby mode with one radial node in the middle convection zone here. The flow pattern can be schematically illustrated like this. And in the bottom, I also show the eigenfunctions of the thermal Rossby mode with north-south antisymmetric Z vorticity. And their dispersion relations are computed like this. And what is interesting is that when they are plotted all together in the single dispersion diagram extended to -m, we see that these two, the dispersion relations of these two oppositely propagating modes are actually connected with each other across m equals 0. And this shows that which means that these two modes are actually mixed with each other. And this kind of mode mixing can be understood in analogous to the so-called Yanai waves. So Yanai waves are the mixed modes between retrograde propagating Rossby and prograde propagating Kelvin modes. But here, so what is shown is that it's a mixed mode between retrograde propagating equatorial Rossby and prograde propagating thermal Rossby. So it's it's a newly discovered mode. All right, so that's the results from the ideal case. And now I'm gonna examine the effect of turbulent diffusivity, turbulent viscosity on the equatorial Rossby mode. So here I show the eigenfunctions of the n equals 0 equatorial Rossby mode for different values of turbulent viscosity. So from left to right, I increase the value of nu. So for weak, so if there's no viscosity, there's the radial dependence of the equatorial Rossby mode can be described by r to the m. This can be shown analytically by assuming the radial force balance between the Coriolis force and the pressure gradient force. But when the moderate amount of viscosity is included, this radial force balance it no longer holds, and it leads to a diffusive momentum flux, downward diffusive momentum flux. And this is why, as you can see, as we increase the turbulent viscosity, the radial profile of the equatorial Rossby modes is drastically changed. They tend to be more and more confined near the base of the convection zone. So this is a significant result because this r to the m dependence has been implicitly assumed in many studies. So next, the effect of solid differential rotation. So here I show the eigenfunctions of the equatorial Rossby for with the solid differential rotation included, the differential rotation profile taken from the global helioseismology. On the top, I show the eigenfunctions of the n equal 0, and on the bottom, n equal 1. And this black solid curve shows the location of the so-called critical layer, critical latitude, where the phase speed of the Rossby mode becomes equal to the local differential rotation speed. And you can clearly see that the eigenfunctions are strongly distorted at the critical latitudes. And we can also see that substantial radial motions are driven there around the critical latitudes, even though the equatorial Rossby modes are quasi-toroidal in the ideal case. And this has a substantial implication because this leads to substantial Reynolds stresses around these critical layers. Another interesting thing is that the observed sign drop of the latitudinal eigenfunction that I mentioned earlier could be explained by this critical latitudes. So here I show the latitudinal eigenfunction of the equatorial Rossby with the solar differential rotation for m equal 8. And you can see that this the sign drop at middle latitudes can be well reproduced. All right, so the question that comes up our mind is that, so are the observed, the equatorial Rossby modes observed on the sun, are they n equal 0 or n equal 1? So here I show the dispersion relation plot of the n equal 0 mode by red and n equal 1 modes by blue for the realistic model, including the differential rotation, viscosity, and so on. And we can see that, and these white points denote observations. And we can see that the observed frequencies of the Rossby modes largely lie in between these two. So for this is m equal 3. So for m equal 3, we can, maybe we can confidently label it as n equals 0 mode. But for the higher m modes, we cannot say anything conclusive. Maybe the solar Rossby modes could be a mixture of these two. But the important thing is that if they have the contribution from n equal 1 modes, it is interesting because the n equal 1 modes is the mixed mode with the thermal Rossby, and they are partially convective. The realistic, so there's a question about the turbulent viscosity, diffusivity. So so we don't know. So by realistic, I mean, so actually I used the value of 10 to 12 square centimeters per sec. And this is the value typically, this is the value expected from the mixing length theory. But but as mentioned, it's we don't know the exact values of turbulent viscosity in the sun and in its radial profile. So all right, okay. All right, so next, let's talk about the high latitude modes or topographic Rossby modes. So they are very interesting because we found that they are very, very sensitive to the latitudinal entropy variation. But why do we need to care about this? So the sun's differential rotation is known to deviate from what the Taylor-Pradman theorem expects. So the angular velocity is not like cylindrical, but it's slightly inclined, it's conical. And so in short, the sun's convection zone should be slightly baroclinic. And we are interested in how this baroclinicity affects the properties of the inertial modes, especially the high latitude modes. So here I show the, so this is the case. So, okay, sorry. So what we did is to change the amplitude of this latitudinal entropy gradient term by hand, and then track the topographic Rossby mode. So this is the eigenmode where the latitudinal entropy gradient, this dsd theta term, is switched off. And what we get is this topographic Rossby mode. The z vortices are almost parallel to the z-axis, and the mode is stable. So here, so this is the eigenfrequency of the m=1 mode as a function of frequency and growth rate, and the mode is stable. But as the dsd theta term is increased, we see that the mode becomes more and more unstable, even though the background stratification is convectively neutral. So that's why we sometimes call them baroclinically unstable modes, or yeah, baroclinic modes in short. So when the baroclinicity is substantially strong enough, we have these z vortices are very much inclined in longitude, and at the surface we can see a clear spiraling pattern, which is very similar to what we observe on the sun. So in order to reproduce this spiraling pattern, observed spiraling pattern, we need to include this dsd theta baroclinic term. The linear dispersion relation of these baroclinically unstable modes shows a very, very good agreement with the observed frequencies of the high latitude modes. And another interesting thing about these high latitude modes is that they transport thermal energy. They transport heat from pole to the equator. So in the nonlinear regime, it is expected that this latitudinal heat transport can lead to an instability, the baroclinic instability. All right, so that's the major results from the linear calculations. And now let's move on to the nonlinear studies. So the main, so our main interest is how these inertial modes behave in the nonlinear regime. So to this end, we have carried out a fully nonlinear rotating convection simulations with a solar-like setup without magnetic field. The differential rotation generated looks like this. And we have run the simulation for 15 years after the differential rotation becomes statistically stationary with the temporal cadence of 5 days. And then we compute the power spectrum to characterize the mode. And then we extract the eigenmodes, the eigenfunctions using the singular value decomposition method. More details can be found in this published paper. So we found that the most dominant mode in the nonlinear calculation are the thermal Rossby modes. So here I show the equatorial power spectrum of longitudinal velocity at the surface, and the overplotted in red shows the linear dispersion relation. So we can clearly see that the thermal Rossby modes exist very, very dominantly in the simulation. And here I compare the eigenfunctions. So the top ones are the eigenfunctions computed by linear analysis, and in the bottom I show the eigenfunctions taken from nonlinear calculation, extracted from the nonlinear calculation. And you can see the agreement between these two is striking. And we also found that these thermal Rossby modes transport substantial amount of enthalpy and angular momentum. And their contribution can account for about 65% and 40% of the radially upward enthalpy flux and the latitudinal, the equatorward angular momentum flux when summed over all azimuthal orders. For the equatorial Rossby, we also found the equatorial Rossby modes in our simulations. So this is the power spectrum near the base of the convection zone. And you can see that the power ridge exists along the linear dispersion relation. And again, the eigenfunctions, when you compare with the linear calculation, the eigenfunctions show a very, very good agreement. So this is the eigenfunction for n equal 2. For higher n, we see that, so this is the same power spectrum of latitudinal velocity, but at fixed m of 16 as a function of radius. And you can see that at higher m, the power of the equatorial Rossby tends to be more confined near the base of the convection zone. So if I plot the radial profile of the eigenfunction for different m's, it shows that, so for a lower m, the radial dependence is like an increasing function in radius, but at higher and higher m, it switches to a decreasing function in radius. And this trend is well expected from the linear theory, as I explained earlier. So this can be explained in terms of the turbulent viscosity. But in this nonlinear calculation, the turbulent viscosity largely comes from the turbulent mixing of momentum and entropy. And we also confirmed the existence of the mixed Rossby modes in our nonlinear calculations. So this is the power spectrum of longitudinal velocity, north-south antisymmetric component of the longitudinal velocity at the surface. And you can see that the prograde propagating power ridge and retrograde propagating power ridge and prograde propagating power ridge are connected with each other when they are plotted in the extended power spectrum. And when plotted, and when the eigenfunctions are extracted and compare with the eigenfunctions of the linear calculation, we can clearly see that. So this is a very good confirmation of the mixed Rossby modes. All right, and the amplitudes. So amplitudes can only be studied with the nonlinear calculations. So in our model, these inertial modes are stochastically excited by a turbulent convection and also damped. The nonlinear saturation also comes from turbulent convection. So we didn't use any trick to control the amplitude. And this is the velocity spectra for different modes for different m at the surface. And we can see that the dominant contribution comes from the thermal Rossby, and the equatorial Rossby are the weakest, with the n equals 0 equatorial Rossby. But we see that when the observed amplitudes of the equatorial Rossby are plotted, they are comparable in amplitudes. So this implies that also in the sun, the equatorial Rossby modes are not self-excited, but simply random stochastically excited by convection. Right? So far, so good. All right. We also see the topographic Rossby modes or high latitude modes in our nonlinear calculation. So here I show the m=1 mode extracted from the numerical model, but we couldn't successfully reproduce the spiraling pattern and the observed dispersion, the observed frequencies are not well reproduced. And we think this is due to the lack of latitudinal differential rotation and the latitudinal entropy variation in our numerical model. And these are really hard to control in the rotating convection simulation models because, yeah, everything is self-consistently generated. And this is why we needed to resort to the mean field modeling. So in mean field approach, we can largely control the outcome. We can largely control the resulting differential rotation and latitudinal entropy profile by parameterizing the turbulent transport processes. So that's the last topic of this talk. So in the mean field calculations, so note that we don't solve the turbulent small scale convection explicitly. All of these turbulent processes like convective heat transport or convective angular momentum transport, they are somehow parameterized and given in the model. And in order to control the latitudinal entropy, the baroclinicity, and the differential rotation, we parameterize the lambda effect, and we change the subadiabaticity in the overshooting layer as a free model parameter to change the baroclinicity of the system. So from case 1 to case 3, I have increased the baroclinicity of the model so that you can see the enhancement of the latitudinal entropy variation. The differential rotation is also enhanced accordingly. All right, so this movie shows the temporal evolution of the system from case 1 to case 3, from top to bottom. So on the left, I show the non-axisymmetric component of the longitudinal velocity at the surface. And in the middle, I show the differential rotation and zonally averaged entropy profile. And on the right, I show the time evolution of the volume integrated kinetic energy for different M modes. The black one is the mean flow, the kinetic energy of the mean flow, which is basically the differential rotation kinetic energy. So we can see that, so in case, so in case one is not very interesting because the baroclinicity is too weak to excite the modes. So all the modes are very weak in amplitudes. And in case 2, we have moderate latitudinal entropy variation. And this makes some mode self-excited. So the m=1 mode now pops up because it is excited, baroclinically excited. But its mode amplitude is still too small, too weak compared to the m=1 mean state, so that it just saturates at some point. In case 3, on the other hand, we can see that the baroclinicity, the baroclinicity, the latitudinal entropy variation is so much strong so that all the modes are excited from m equal 1 to m equal 5. And especially the m equal 1 mode is very, very much excited, so that its amplitude becomes very close, is comparable to the mean state, the mean kinetic energy. And then it leads to an instability of the mean state. Because these modes can as I said, these modes can transport heat from the pole to the equator. So this is the sense to alleviate, to relax the imposed latitudinal entropy variation. So these modes transport heat, and then the baroclinicity is substantially relaxed. And so this is the 3D structure of the baroclinically excited mode. And you can see that the mode in a strong temperature perturbation. Sorry, it's a so this 3D volume rendering shows the non-axisymmetric components of longitudinal velocity and temperature perturbation. And I'm saying that the temperature perturbation, strong temperature perturbation, is always associated with the mode. So this mode is very thermal thing. And again, we also argued that the observed spiraling pattern, spiraling flow pattern of the sun can be very, very nicely explained by this baroclinically excited, baroclinically driven high latitude modes, baroclinically excited topographic Rossby mode. And they are not only, like they are very important because as I said, as I explained this movie, because they play a very important role in modulating the baroclinicity in the convection zone. And it also indirectly controls the amplitude of the latitudinal differential rotation in the sun and stars. And this is a very important point, I think, is because in most of the numerical model, the mean field model, to study the stellar differential rotation and meridional flow and so on, the models are essentially 2D. And these non-axisymmetric inertial modes contributions are simply cannot exist, they are ignored. So so we warn that the 2D models can largely overestimate the amplitude of differential rotation. In the 3D models, when the baroclinicity is substantial enough, they excite inertial modes, and they can transport substantial amount of heat and angular momentum to change the mean state. And this is a very interesting and important point. Another interesting thing is that, so we observe these baroclinic modes on the sun, and which implies, so this can be regarded as an observational evidence of the latitudinal entropy variation in the sun's convection zone. And this corresponds to the observed amplitudes. So this corresponds to the latitudinal temperature variation of about 7 Kelvin in the middle of the convection zone, which is much too small to be directly measured. But using this inertial mode argument, we can still infer the existence of this very, very tiny latitudinal temperature variation in the sun's convection zone. All right, so that's basically all I have. So here's the summary slide. So so recently, a bunch of inertial modes are observed on the sun, and So all of these numerical modeling that I described today, so these are like the first step towards the inertial mode helioseismology. And there are also many more interesting things going on. So yeah. So I'm not going to read all of these, but I just did it. So, okay, thank you very much for your attention. And that's all. I'm happy to answer the questions.